Welcome back. In the past lecture, we have seen a couple methods for machine learning. In today's lecture, we're going to see another one, which is tree classifiers, which is another method that actually has different concepts and different mechanism. We're going first to define what are tree classifiers and talk a little bit about the history of this method. We're going to provide a toy example and show what a tree classifier would look like on that example. We're going to talk about the splitting criteria in one of the most famous algorithm in building trees, which is C4.5, proposed by Quinlan. We are going to talk about how numerical features are handled, some pruning strategies, and also alternative methods such as CART. We're going to talk a little bit at the end about practical considerations and the pros and cons of using tree classifiers in machine learning. So first of all, tree classifiers is one of the most popular classification methods in machine learning. It's easy to understand and easy to implement because it has a simple algorithmic approach to it. There is no assumptions we need to make about whether we are going to deliver a linear model or not. So we just take the data as it is. Historically, there were two classes of tree classifiers in the literature. They were both invented in the computer science community by Quinlan. There was a whole Quinlan series between 79 and 83 of algorithms, including ID3 and C4.5 family of algorithms. And also in the statistics, such as CART, classification and regression trees, proposed by Friedman in 1977. There were many refinements afterwards in the mid-90s, for example, including pruning and handling numerical features in the Quinlan family of tree classifiers. Tree classifiers has been applied a lot. This includes applications in botany, in medical research, and in computational biology, to cite a few. So how does it work? Let me first point out that the terminology tree is purely graphic. So when we build tree classifiers, what we are building is a kind of decision tree that is grown from the root downward, in the sense that, first of all, we start with the root in which we have all our examples to classify, so as we build the model. And then we're going to send these examples down the tree using the concept of information entropy that allows us to build a classifier that makes a good decision model for the data. The general steps of the algorithms to build the tree are as follows. First of all, we're going to start with the root node in which we have all our examples. Suppose our bananas and oranges. We're going to start with the set of all fruits at the root, and we build the decision tree downwards. So once we put all the data in the root, we're going to do a greedy selection for the next best features that actually splits the data correctly. So the splitting criteria here is based on the node purity. So I'm going to go through the features one by one and select which ones are splitting the data in the best possible way, which means that by picking this feature, I'm going to achieve node purity, which means that nodes that are either from one class or the other one. That's in step 2. And finally, in step 3, we're going to assign the class majority to the leaves of the tree. Okay, so these are the main steps, these are the general steps. So let's recall first the classification scenario. We have data, and the data is a set of feature values with a label, where the values are in RD, and we have the label, which is a discrete value. So the label could be +1 and -1, or 0 and 1 in a binary classification scenario. Okay, the classification aims to find the classification function f that maps the input to the output, or otherwise the features to the label. In the case of tree classifiers, we're not building a function f. What we are building is a model that is a tree, right? And there is no need for the features xi to be in RD, so there is no need to turn any categorical feature into a numerical feature. So we just take the data as it is, and we build a tree in lieu of building a function f. Here's an example about job hiring. Suppose we have historical data about applicants who applied in a given company for a job. So we have information, so we have the applicants, the list of applicants from the past. We also have features describing these applicants, and these features are highest degree, work experience, their favorite programming language, and whether they needed a work visa or not. We have the label, which is whether the company ended up hiring them or not. The goal is to build a decision tree that will help us decide when we have a new applicant, whether we should hire the applicant or not. So in other words, suppose we have a new applicant with a master's degree who works on user experience design, whose favorite programming language is Java, and who does need a work visa. Should we hire the candidate or not? By applying a tree classifier building method, we obtain a tree similar to this one that help us decide for this new applicant whether we should hire him or not. So the applicant has as favorite language Java. So I'm going to go through the tree, the first node. The favorite language is Java, so I'm going to go through this path, the left-hand side. Given that this value for the feature favorite language, the next feature to test is highest degree. The highest degree is master, so I'm going to go through this path. And this path leads us to the leaf that says, yes, we should hire the candidate. So the answer is yes. So you could see that this hierarchy was obtained by using the data. The way this tree classifier was built is by first considering all the examples. So the example we have eight of the applicants in the past were hired, and 6 of the applicants were not hired. So we start with this large set of applicants. We're going to need to pick one criteria or one feature value to split this data. So again, it turned out that the feature that were selected was favorite language. If favorite language is Java, then this data will be split into left and right? On the left side, we have 6 applicants who were hired and 1 applicant who were not hired. And on the right side, we have 2 applicants hired versus 5 who were not hired. So this seems like doing a pretty good job at splitting the data between hired and not hired. So, and so on and so forth. We're going to go again, do the process, and pick another feature value for which we split the data, with which we split the data. So the next one that was picked is highest degree, and this highest degree would have 3 possible values: bachelor, master's, and PhD. And it turned out if you pick this feature, you're going to have nodes that are all pure, which means that they have examples of one specific of the classes. So it's clear that splitting criteria in this kind of algorithm, and we are talking here specifically about the line of algorithm that is C4.5 or ID3, is the central choice is really the splitting criteria. How do we pick the next attribute or the next feature to split on? So we are looking for some criteria that measures the homogeneity of impurity of the examples in the nodes. So you could see here that we were quite happy to see that in this node specifically we have 6 hired versus 1 non-hired. So we're looking for some criteria that help us split the data so as we put them in buckets of classes. So we are looking for some criteria that actually help quantify the mix of classes at each node. The maximum is reached when there is an equal number of elements or examples from each class in the node, which means that there is a high homogeneity of, or the node is impure. And we want this measure to be minimum if the node is pure. So we have only one class in the node. A perfect measure for this kind of situation is commonly used in information theory and is called the entropy. So the entropy will be measured for node S. So given a node, given some node S, the entropy will be measured by taking into consideration the proportions of positive and negative example in the node. So the entropy of S is defined as minus proportion of positive log 2 of proportion of positive minus proportion of negative log 2 of proportion of negative in the nodes. So this measure will tell me what is the mix in the node. The best way to understand how the entropy can measure the purity of a node is to plot the function of entropy. So you could see that the entropy is at its maximum whenever we have a perfect balance of positive negative, and this could be seen at this point here. So here, on the x-axis, we have the proportions of positive examples. When it's 0.5 means that we have as much positive examples as negative examples, and in this case, the function would be at its maximum. So this is responding to the criteria that we are looking in this, and the kind of function that could help split the data. The function is at its minimum whenever we have a pure node. So this is at this point here where we have only positive examples, or at this point here where the proportion of positive examples is 0, which means that we only have negative examples. So this function is the perfect function to measure this purity of nodes. In general, if we have C classes, we can generalize the entropy function for node S as the sum of minus pi log 2 of pi, where each of the pi is the proportion of one of the classes in the data. We use a measure called information gain that measures the expected reduction in entropy caused by partitioning the examples according to the attributes. In other words, the gain for some node S, given some feature or attribute A, is the entropy at the node A minus the entropy at each of the nodes that are children of A if we split by A and each going through all of its features. In other words, it's the entropy of S minus the entropy weighted by the size of each of the nodes. So going to sum over all possible entropies for all possible values of the feature A, but to weight that by the size of each of the nodes as compared to the whole size of the node S.